It is actually Easter for those of you who celebrate it. So happy Easter for those of you who celebrate Easter, and happy Passover for those of you who celebrate Passover, and happy Sunday for those of you who celebrate nothing. I'm making this video because I was quite inspired by the mathematics devotional for April 12th, and it says, "Our mathematical models of physical reality are far from complete, but they provide us with schemes that model reality with great precision, a precision enormously exceeding that of any description that is free of mathematics." Now, what that means is basically we should be using mathematical models when we can. And I bring this up, and I was inspired to do this because of this quote. Because in the news right now, in the midst of the coronavirus, people are kind of downplaying the mathematical models, and they're saying, well, the models had said this, and now something else is happening. So what is a mathematical model? What is mathematical modeling, and how is it used? I'm going to explain mathematical modeling a little bit and how it's used. And in doing so, I'm going to use an example. So I drew very, very poorly a 6-sided die right here. And I'm going to talk about 6-sided dice and 12-sided dice. And here's what I did. I actually made a mathematical model. I went on to Excel, and maybe I'll just kind of explain what I did real quick. I wanted to know what the mean absolute deviation is from if you roll 2 dice that are numbered 1 through 6. I'm not sure where the last egg is hidden, kiddo. I'll have to come and help you in a little bit. Oh, look in the tissue box. So what I did was I rolled 2 dice, and when you roll 2 dice, you'll realize that you can get a number between 2 and 12. And then I rolled a 12-sided die, which has all the numbers between 1 and 12. And if you do that, you can record your results. And let's see. What I did was, well, I'll show you real quick. To simulate rolling a 2-sided dice, I say equals random between, and then I said 1 and 6. And when it does that, you get a 4. Well, I can now do that for this one too. So this would be die 1, and this would be die 2. And then what I said was equals the sum of those 2 dice. So all I've done was I've created a little simulation where 2 dice are rolled, and then it adds it up. And then what I did was I recorded, I did this for 300 samples, I believe. Let's see. 301 samples, I believe. So what I did was I found out what would happen if I rolled 2 dice. What would I get? And then I found the sum, and I found the average score. All right. Now the mean absolute deviation is the difference between what you actually got and the average. And then what you do, or mean absolute deviation. And then what you do is you sum all of these up, and you find the average, and that's the mean absolute deviation. So how far away from the mean, what's the average distance that the scores are from the average? I know that kind of sounds weird. So you can see my average was 6.87. And these are all the distances from 6.87. And then this is the average of all those differences. And you can see it's a little bit less than 2. And if you look at my bar graph here, you'll see that the number 2 came up 11 times. The number 3 came up 21 times, so a little bit more. Number 4 came up 20 times. 5 came up 33. 6 came up 44. 7 came up 64. 8 only came up 28. And here's a point. This kind of makes sense, because if you think about two dice, the chances of getting a 2 is the only way you can get a 2 is a 1 and a 1. And take a look at 12. The only way of getting a 12 is a 6 and a 6, and they only came up 7 times. But you would expect 8 to come up quite a bit. 7 you'd expect to come up the most amount of times because there are 6 ways of getting a 7. There are 5 ways of getting 6s and 5 ways of getting 8s, but you can see this is only a model, and so this is what is kind of expected to happen, but doesn't necessarily mean it's going to happen. If it was exact, it would be a nice symmetrical bell curve. The 8 not coming up is because experimentally, that's not what actually happened. And that's where models get the bad rap. Yes, you can run a model, and that what should happen and what actually happens are two different things. Now, remember, I just said that the average deviation, the distance away from the actual average, was only 2. When I go to a 12-sided die, first of all, you can see it's a lot more uniform. I did the same things, except I did between 1 and 12. I got an average was 6.4, which makes sense because 6 is in between 1 and 12. It's halfway between. And in 2 dice, I had an average of 6.8. So that does make sense. Both of them make sense. But my mean here, my mean average deviation was more. It was 3. It was nearly 3. Here it was nearly 2. And you might be wondering, well, why should the mean average deviation be greater? But if you think about it, the chance of getting a 1 on a 12-sided die should be about the same as getting a 2. Not should be about the same, should be the same as getting a 2, because there's only 1 12, or 1 1 on a 12-sided die. There's only 1 2 on a 12-sided die. There's only 1 3, etc., etc. So you can see all of these should have come up about the same amount of times. Coincidentally enough, 7 7, which was the high point on a 2-sided die, ended up being the low point. But once again, that doesn't really say too much about this, except in this experiment, after running 300-something samples, the 7 just came up only 18 times. So, let's see, what is equals 301? I think I end up with. So each of them should have come up about 25 times, and you can see some came up a little bit less, some came up a little bit more, but they were all around that. However, the difference was, the mean absolute deviation was 3. And so you can see models give you an example as to what should be happening, and this makes sense. And I can run this over and over and over again. Oops. You can run this over and over and over again. Of course, now that I say that, I'm not really sure how. Interesting. Oh, I know how. I wonder if I just do that. Yeah. And it'll keep coming up similarly each time. But my mean absolute deviation keeps hovering around 3. And look at this. Once again, still a little bit above 3, a little bit below 3, just a tiny bit below 3. Look how uniform that was. Just a little bit above 3, etc., etc. Even this one, which is a little bit more below 3, it's still the graph is still very uniform. Once again, if I go back to here and I mess around with it, this will probably hover around 2, which means all of my rolls are around 6.98, which is 7. Approximately 7. My average still is about 7. And look, all the mean distance is about 2 units away. And that stays true. Even when we do this, you can see the graph always maintains more or less the bell shape, but it is a model, and so therefore it's not a predictor. It is a predictor, but it's not an oracle, and it's not a prophecy. It's not going to always be exact. You can see here the number 6 came up more than the number 7. But once again, when I run another model, the number 7 comes up more. So in any event, if you're wondering what they're talking about with mathematical models, and none of that seemed to make any sense, and you never really understood the mean absolute deviation, don't feel bad. Lots of people don't. But I hope this video helps. Like I said, enjoy your Easter or Passover or just your Sunday afternoon. All right. Thanks. Bye-bye.